Hello everyone, my name is Ranim Qaddura. I'm gonna present for you the paper titled EvoCluster, an open source nature-inspired optimization clustering framework in Python by Ranim Qaddura, Hussam Fares, Ibrahim El-Jarrah, and Pedro Castillo. Clustering is an unsupervised learning task which aims at grouping similar points into the same cluster and dissimilar ones into different clusters by exploring common relationships between them. Clustering is essential in many applications. This is one of the applications where customers are grouped according to their annual income and spending score in a mall. Segmenting these customers is important for future reasoning and decision making. Nature-inspired meta-heuristic algorithms are commonly utilized for performing partitional clustering tasks. They are proven to be efficient for multiple scientific and engineering domains. These are some well-known and recent nature-inspired meta-heuristic algorithms such as GA, PSO, GWO, and all the others. The main advantage of using these algorithms in clustering is the ability to explore and search for better grouping of data to clustering results. Many frameworks and libraries can be found in the literature that can be used for performing the clustering tasks. Some popular examples are Weka, Elki, and scikit-learn. Some general purpose frameworks and libraries were developed to facilitate the use of nature-inspired meta-heuristic algorithms. EVO-ML is one of the recent open-source Python frameworks that includes well-known and recent optimization algorithms. EVO-ML FS is another version of EVO-ML for feature selection. NumPy is Python micro-framework for building nature-inspired algorithms. Other popular frameworks include Deep, ECJ, and all the others. To the best of our knowledge, we found only one framework for clustering with evolutionary algorithms, which is Leek. Leek is implemented using C++. It includes 23 evolutionary algorithms for partial clustering. Users tend to use other languages which have more libraries and packages such as Python. Is only different variations of the evolutionary operators and do not include other algorithms. So there is a need for a framework of nature-inspired meta-heuristic clustering optimizers, which is not specific to the evolutionary algorithms. So we're introducing EvoCluster, an open-source nature-inspired optimizing clustering framework in Python. EvoCluster is implemented as a flexible framework, which includes several nature-inspired meta-heuristic optimizers for performing the clustering task. It is an extension to the EvoCluster framework, which is implemented to serve any optimization problem. EvoCluster is extended in which the algorithms are customized for the partitional clustering task. The current implementation of the EvoCluster framework includes 10 meta-heuristic optimizers, 30 datasets, 5 objective functions, and 12 evaluation measures. To the best of our knowledge, EvoCluster framework is the first framework in Python for clustering data using the selected meta-heuristic optimizers. Our motivation is to provide an open source and cross-platform framework for clustering using nature-inspired meta-heuristic algorithms, as there is not much available free code for researchers in this area. We aim at providing an open source framework which is simple and user-friendly. Since Python is a rapid development language that is recognizably growing in the data science machine learning fields, Python was selected for implementing this framework. It is comprehensive and easy to understand and use. It is scalable and can be customized to provide more algorithms, evaluation measures, objective functions, and more datasets. It is time efficient and provides high quality results. It is suitable for experienced and non-experienced users. The framework consists of 6 main components. The first one is the optimizer, which is the main interface of the framework. Users can select the set of optimizers, datasets, and objective functions that they prefer for running their experiments. They can also select the evaluation measures for evaluating the results generated from the framework. They can also specify the main parameters that are common for most optimizers, which are the number of iterations and the population size. The number of runs can also be determined through this interface. The implementation of 10 optimizers is currently visible as a separate file for each in the framework. The optimizers that are available at the time of writing this paper are genetic algorithm, particle swarm optimization, Salp swarm algorithm, firefly algorithm, gray wolf optimizer, well optimization algorithm, multiverse optimizer, moth flame optimizer, bat algorithm, and cuckoo search algorithm. The framework consists of the implementation of 5 objective functions, which are used to optimize the individuals at each iteration. The objective functions that are available at the time of writing this paper are sum of squared error, silhouette coefficient, total within cluster variance, Davis-Baldwin index, and Dunn index. The framework consists of the implementation of 12 evaluation measures, which are used to measure the quality of results. The evaluation measures that are available at the time of writing this paper are purity, entropy, homogeneity score, completeness score, V-measure, adjusted mutual information, adjusted rand index, sum of squared error, silhouette coefficient, total within cluster variance, Davis-Baldwin index, and Dunn index. Most common and well-known datasets used for clustering can be found in the framework. The list of datasets that are available at the time of writing this paper are summarized in this table. They are gathered from scikit-learn, UCI Machine Learning Repository, School of Computing at University of Eastern Finland, Elke, Kiel, and Naftali Harris blog. The results obtained by running the framework are gathered in 3 types of CSV files and 2 types of plots. They are average results file, detailed results file, best individual labels file, convergence curve plot, and box plot, which I'll describe shortly. The first file is the average results file. This file gives average results of running the framework on the selected optimizers, objective functions, and data sets. You can find the average execution time, the average value of the evaluation measure, and the average value of the objective function at each iteration for each combination of the selected optimizers, objective functions, and datasets. This file is the detailed results file. It gives detailed results for performing each run of the framework. You can also find the execution time, the value of each external measure, and the value of the objective function for each iteration, but for each run. This file is the best individual labels file. It includes the values of the labels obtained from the best individual at the last iteration of each run. This figure is the convergence curve plot. After running the convergence curve script, a separate plot is generated for the convergence curves of the set of selected optimizers for each objective function and each dataset. This figure is the box plot, which is commonly used for summarizing a set of data measures on an interval scale. The framework generates the box plot to represent the evaluation measures of each dataset for several runs of the framework, where each box represents one of the selected optimizers. The framework is successfully published at EvoStar 2020 conference and at the proceedings of the Evo Applications 2020. The source code is available at GitHub, Google Colab, and EVO-ML.com websites.